Hello and welcome to another LeetCode problem. We're going to be doing count Univalue subtrees, and it's the premium problem of the week for this week. So in this problem, given the root of a binary tree, return the number of Univalue subtrees. A Univalue subtree means that all nodes of the subtree have the same value. So for this, okay. So we have this tree. And so what they mean by a Univalue subtree is it can be any subtree with a root, and like the rest of its nodes have to have the same value, but it doesn't have to be a complete tree. Like this could still be a subtree even though there is no left node. And so from the example, you could see that any leaf node is always going to be a subtree because it's going to be a tree of length 1, so it's always going to be a subtree. Now, let's think about like what we need to be doing. So the easiest way to do problems for trees in general is going to be recursion, but like what recursion are we going to have, right? And so it's pretty straightforward. So what we can just do, there's a few ways to do this. I'm going to do this with a global variable. So we're going to take a global variable called like result, right? And we're going to just there's a bunch of tricks you can do. You can have it be non-local. You can have result be an array of length 1, and then just update the value there. You can do a bunch of different things. But regardless, so what we're going to do is we're going to have a traversal function that's going to traverse all the way down to like the leaves. And then simply when we get to a null node, we can just return. So we're going to have a few return values. We're going to have a return value that is actually the value of all of the nodes in the tree. And so I'll show you what that looks like. And then we're going to have another return value like -infinity, meaning, you know, we had a null node, but it's still fine. And then we're going to have another return value infinity, meaning like the rest of the subtree is no longer, you know, a unique or a unival tree or whatever the name was. And so let's take a look what this is going to look like. Let's take a look at our result. So we're going to have a result right here, and we're going to traverse all the way down. So we're just going to traverse all the way down. So like, for example, let's just say we traverse left, right? So we're going to go over here, then we're going to go over here. Then we're going to be at this node. This node is going to have no children. But what I will do is I will still go into the children. And so when you go into the children, these children will just return -infinity. And so the return for this left will be -infinity. And this right is going to be -infinity. And then what you simply do is you make a left and a right value for the return values once you recurse back up. So we'll recurse back up, and we just have to check, okay, is the root value the same as the left and right value, or it either has to be the same as the left or right value, or those values have to be -infinity, meaning any value works. So that's how I'm going to symbolize it in mine. You can do it in a bunch of different ways, but so for this first example, you're going to return up to -5. You're going to check the left and the right, and you're going to compare it to itself. Because they're both -infinity, that means they're fine. Like we don't. If they were something else, then it wouldn't be fine. Like if they were 6 or something. So that means this is a Univalue subtree, and so we would have 1 here. Now we would return back up here, and then the number we're going to be returning is going to be the value of the Univalue subtree. So if some other, like if some of its nodes were infinities, we're still going to return the value of the nodes. If it's a null node, we're going to turn -infinity. But if it's a actual node that we care about, we're going to return the value. So we're going to return a 5 up here. Now we're going to recurse right, and we're going to do the same thing on this node where it's going to have 2 -infinities. And so when we check the -infinities with itself, that'll be fine. So we're going to add 1 to the result. Now we're going to return a 5 up here. Okay, and now that we return back up to this one node up here, we're going to check the one to the left and the right, and now these are no longer -infinity, so we actually have to compare the values. And so because the one has to be equal to both the left and the right, and it's equal to neither, that means this is not a Univalue subtree. And now when we return, we need to send a message to the node that called it saying like, now this is no longer a Univalue subtree. And so what I'm going to use to represent not a Univalue subtree is actually going to be infinity. I just want values that like we don't have. So I'm going to return infinity up here. And now here we need to go to the right child, and then we need to go to the right child again. This will be a Univalue subtree, same kind of thing here, where it'll have a -infinity and -infinity for the 2 nodes. So then we're going to add another one here. we're going to return the value 5 up here. Now we're going to compare this 5 to its left and right child. So it only has a right child, which is 5, which is fine. And then its left is going to be negative infinity, which is also fine. Like I said, you either have to have the values be equal or they have to be negative infinity. So this is a fine univalue subtree, this one right here. And so we're going to add another one. And now we're going to return, finally, the value of this 5. So we're going to return the value of this 5. And remember here we returned infinity, symbolizing like everything we're returning upwards is no longer going to be a univalue subtree. So this right child is equal to the node, but this left child is infinity. So therefore, that's not a univalue subtree. The left child either has to be 5 or negative infinity to be a univalue subtree. And that's pretty much all you need to do. You just recurse down to the nodes. You have something to symbolize a any value state, and then you have something to symbolize a nothing from here will work. Like let's say, like once you get an infinity and you start returning up, you're never gonna get a univalue subtree to anything you return. Like once your subtree is not good, it's never gonna be good anymore. Hopefully that makes sense why that is. And yeah, so like let's say we were to return up here, we would always just be returning infinity, 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 and then nothing would work. And that makes sense, right? Because when we're recursing up, that means like the root and all of the children, which we just came from, have to be the same value, and we're sending a message saying they're not. Okay, so that's pretty much everything we're gonna need to solve this problem, and now let's do it. So like I said, I'm gonna have a result value. You could declare it in a bunch of different ways. So I'm just gonna declare it, actually I need to reset the code. Okay, so what I'm actually going to do is I'm going to declare it here, and I'm just going to make it an array of size 1. You can do a bunch of different things. So you could do this. You could give it a value. You can make it non-local. I guess I'll do that just to show the non-local. So we're going to say result is 0. Now we're going to have a helper function. We'll call that traverse, and then we're just going to have a node. So remember, if the node does not exist, so if not node, we just return negative infinity. Right. Okay, now if the node does exist, we need to go to the left and the right. So that's pretty straightforward. Left equals traverse node dot left. Right equals traverse node dot right. We're going to visit the left and the right first before comparing to the root. And so the left and the right have to either equal the root or they have to be negative infinity. Either one works. And so now we just have an if statement here. So if left equals negative infinity, right? So negative infinity, or left equals the value of the node, and so that's going to be node.val. Then it needs to be both of these. So the left needs to equal one of these, and then the right needs to have the same thing. So we need to have an and here. We can probably just do like something like this because this is going to take a lot of space. So we can do something like this, and then like this. Okay, let's just copy this code over here. So right needs to either equal negative infinity or the value of the node. I think that's lined up correctly. Yeah. And so now we do this. So if that's the case, that means we do have a valid unival subtree. And so we're going to call result. We don't have access to it, so we need to do this. You could also make it a class variable and then call self on it. Either one's fine. Res plus equals 1. That means we have another univalue subtree. And so if this is the case, if this whole, like, let's say we're at this whole thing, if this is a univalue subtree, then we need to pass back up its value, right? So we need to return node.val. Otherwise, it's not a univalue subtree, and so we need to return negative infinity to symbolize to every parent of that we're no longer going to have a univalue subtree. So we can return negative infinity, or infinity here. You can use other numbers, just look at the constraints. So I think this is like negative 1,000 to 1,000. You can use 10,000 to symbolize, or whatever you wanted to. Actually, you can probably just even return, like, because it's Python, you can just return a different type. You can just return like false or something. I think that would work too. But yeah, so now what we need to do is we need to return infinity, right? So, okay. And so now finally we need to call traverse on the root, and we need to return the results. So let's see how many things we screwed up as always. Okay, looks like we did not. Amazing. Okay, so pretty efficient. Yeah, and so the other way you could do this is like you can technically not use a res here. You can probably pass down values and add them up, but I think this is pretty clean. And yeah, if you don't like using this non-local, you can just make it a class variable if you don't want to use that. Okay, and yeah, so I think that's going to be it for this problem. Now let's just do the time and space here. So that's pretty straightforward. For almost all tree traversals, we need to visit every node, so that's going to be big O of n for every node. And space, straightforward as always. So for space, for a balanced-ish tree, it's going to be log n. And worst case scenario, our entire tree is, as always, going to look like this, right? So if our entire tree is not balanced at all, then we're going to have this whole recursive call stack saved in space. And so that's going to be big O of n worst case. But if it's somewhat balanced, it's going to be log n because it's a tree with 2 children. Okay, so that's going to be it for this problem. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.